Welcome back, guys. So, you have learned about the model called logistic regression in previous ones, and that will help us to make prediction based on data. There are two important things which we should focus on: the loss function and the cost function. The loss function tells us how well our model is doing on our training example, while the cost function helps us understand how well the model is doing in our training examples together. So, now we want to use something called gradient descent. So that's the concept that we are going to learn in this video. So what gradient descent is, it helps us do the same thing by starting some initial guess for weight and bias, then adjusting them step by step. We keep adjusting them in the direction that reduces the cost. The size of each step is controlled by something called the learning rate. If the cost function is shaped like simple ball or convex ball, no matter where we start, we will eventually reach the lowest point. To update weight and bias W and B, we use something called derivative, which tells us the slope or steepness of the cost function. If the slope is steep, we are going to take a big step. If that is shallow, then we are going to take a smaller step, and we are going to keep repeating the whole process until the values for weight and biases doesn't change anymore, which means we have found the best ones for our module. So in coding, the slope is represented by dw or w and db for b. So dw for weight and db for bias, and we update w and b by subtracting the small amount based on how steep the slope is. By doing this repeatedly, we can make our model better and better. This might seem complicated, but if you're not familiar with calculus, but don't worry too much about that details right now. The important idea is gradient descent helps us find the best values for weight and bias, making our model accurate as possible. So we'll go through the other example right now. So imagine you have the lemonade stand and you want to make sure your lemonade is yummy enough for all your customers. How do you know if it is the right amount of sugar? One way to figure out is by trying different amounts of sugar in each cup of lemonade at a time until you find the perfect amount of the sugar that everyone is going to like. But if you tried every single possible combination, then it will it will take forever. So that's where something called gradient descent comes in. So it is like the special helper that helps you figure out the right amount of sugar by using clues about how well each cup of lemonade is doing. So first, what we have to think about is kind of the clue what we want to use. Then it is it people saying that is good or not enough sugar. The clue tells us something called cost function. It's like scorecard which will say how good or bad each cup of lemonade is. Then we have to use another tool called derivative to see how steep the slope of cost function is. Imagine you're standing on the hill, and if it is very steep, then you can climb it really fast. But if it is flat, you might not go as far. So the derivative help us figure out how steep the hill is. So finally, we use our clues, the cost function and the slope, which is derivative, to make tiny adjustments, small amount of sugar, until we find the perfect amount for everyone. So that's the whole thing about gradient descent. I hope the concept and the whole idea about what the gradient descent is little bit clear. Now let's dive into the mathematical concepts behind the whole situation. So, uh, in previous ones, we we have been through the loss function. So, loss function measures how well your algorithm outputs uh, y hat I on each of the training examples. Stack up compares to the boundary label of yi, which was this thing. If you guys watched previous videos, then you know what those things are. Of each of the training examples and formula is explained to write. So uh, the formula, I'll write that formula again for this video just for revising the whole thing. So this one is formula. So 1 upon m summation of I equals to 1 to m, and this is the loss function y hat of I, and this is just the y of I. So what does this mean is explained in the previous video. So it will go negative 1 of m summation of I equals to 1 to m and yi log of y hat I plus 1 minus yi log of 1 minus y hat I. So that's what the formula gets expanded to the right. So that's the recap of the last one. So cost function measures how well your parameters of w and b are doing on the training set. So in order to learn to set parameters of w and b, it seems natural to find w and b to make cost function j, which is this thing, as small as possible. So we are going to draw a diagram now. So imagine this thing as a three-dimensional space where we are considering this dimension, like this thing as w, this thing as b, which are weight, bias, and this thing as our cost function, which will be having weight and bias both, and we are having something like this. So what the gradient descent does, it goes downhill. So it we are thinking in the terms of three dimensions, and the curves are going to look much complex than this one, but just for the simplicity's sake, we are going to discuss on this one, and we are going in even on the two-dimensional one just in few time, like a small amount of time. So just know that this point is known as global optimum. This is the so that's where the optimum place of the algorithm, the path it will trace from any point to reaching that point, that's what it will going to be. So that's what all large language models do as well when they are tracing the paths, when they are predicting the words, when they are they have been given the uh, inputs in order to make some changes and follow the directions in the vector space. So that's what happens basically. I'll dive deep into that notion, and it will make sense in upcoming videos, so stay tuned until that. So I hope this three-dimensional thing is clear for now, and we are going to explore the simpler version of this thing. So let's suppose this thing as w, let's suppose this thing as function jw, and uh, ignore b for now. So the function of the w for us is going to be w minus rate of change and multiplied by the derivative of the j of w, like the slope, that exact thing. So what I mean by slope is, let's suppose we take this point, we draw a tangent on this point, and we draw two sides to the tangent on this point, and we just we just take the divide those things, and whatever thing that we are going to get, it's going to, if that is like, subtract those things, and whatever thing that we are going to get, if that is going to be positive, then we are going to keep that thing in this equation. So if this thing is going to be positive, then this equation will be subtracted from the w, and the whole thing will go to left, and that's how it will be. And if we, like, alpha is the learning rate, and it controls how big step we take in the gradient descent. So we'll talk ways to choose learning rates for alpha. So this thing is derivative of change you want to make to parameters w. So when we are going through the writing code for this, we are going to use convention that variable name in our code dw, like this thing, and that will be our derivative term. So when you will write code, you will write something like w equals w minus alpha into rate of change, that is dw. So that's how you will write things in the code, whatever language you're using. So basically dw is the derivative term. That's what you have to understand for now. So even if you guys don't know calculus that much really well, so just know that dw means the differential thing, which is just the rate of change of the slope. That's all it is. So when derivative is positive, you end up subtracting, and it will be something looking like something weight into rate of change into the weight into learning rate into rate of change, which is this thing, which is going to be weight minus alpha dw, and that means we end up taking step down to the left. So that's what it means. And if we start from here, just opposite of this happens, like this will go to the positive, the whole thing will be positive, the equation will be positive, and we are going to take step in the right direction. So that's how it will going to work. So this will make your algorithm slowly decrease your parameter, as we started with the large value of w. So in this case, this scenario, that's what it will going to happen. And if w was in other side, we'd end up subtracting w thing that makes our equation goes to right side. So whenever you go and begin the gradient descent, it will move on to local minimum. So what local minimum is, the thing that I explained to you guys when I was talking about the this thing, global optimum. So that is the local minimum thing. So that's the place when I explained in the two of the examples that the right amount of sugar, or the just the right thing, Now we're going to explore this thing. So djw and dw, this term means just the slope of function, and we want to know slope of function is the current set of parameters. So we know what direction it will go in order to go downhill or onto cost function j. So j is our cost function. So in logistic regression of our function, j, which is our cost function, j of w and b in this case. So w is going to be w minus learning rate into our cost function and the rate that it changes. But here is the one kicker. So we were using this term, like, which is looking like d when we had the single term, but we are using two terms here now. So what what is going to happen right now in this thing? uh, we are going to use something that will be looking like this, but before that we are going to write one more equation where we are subtracting b minus rate of change and the cost function where weight and bias, we are calculating the whole thing, and we are differentiating it in the terms of b. So when we are going to have two things in the function, then we are going to represent that with this thing. So that's what we call as a partial derivative. So that just looks like some weird symbol, but don't worry about it. It is just the normal symbol which explains that you guys are having some more symbols here and you need to do some more things, which just like what we did in the previous some previous time. So that's what it is like. What we are going to write is we are going to replace the d what we wrote here with this thing. So when remember these things, so we are going to write this term when we are having only one term in the cost function or any function that you're differentiating, and we are going to use this thing when you're having two or more terms in the cost function or any function that you are going to differentiate. So that's all for right now. So one more thing, if j is the thing about one variable, then we are going to use this thing. So yeah, that's it. So that's all for now, and we'll explore much more things in later upcoming videos. I hope you guys are doing really nice and be legendary.